So this is the topic of the talk. Now some of the techniques which will be used here is based on the work which Ramesh just mentioned, and that was done with Ramesh. But I have not put the reference here because I mentioned it later anyway. So, and this is a different thing which than what is there in the paper Ramesh mentioned. So we will discuss whether one can have some spatial spacetimes with horizons, and by this term non-singular, I will define it precisely what one means by that. So whether there is some spatial behavior of those kind of spacetimes such that we don't see such behaviors with the usual non-trivial vacuum solutions, which are solutions of Einstein's equations of motion. So that is the topic of our discussion now. Let's first recall a few well-known facts before to put things into perspective. The theory of general relativity is famously known to exhibit black hole solutions, as we all know. Now these black hole solutions, they are solutions of the Einstein's equations of motion in vacuum, and that means they solve this equation where the symmetric Ricci tensor is 0. Now such configurations which are black holes, they are typically associated with curvature singularity, and that means that the curvature scalars for those configurations, they diverge at some point at the interior. For example, if you take the Schwarzschild geometry, the corresponding quadratic curvature scalar, I think that is known as Krishman scalar, although I was not very sure of his name. So that is divergent, and that blows up at the origin, r tends to 0. So typically black hole configurations have this property. Now this is true as long as the metric g mu nu is invertible, and as Ramesh just explained in great detail, that means that the determinant of the metric, if it's non-zero, then all these statements are true, and there is no escape from such singular solutions in that case in the classical theory of general relativity. However, the classical theory of gravity with invertible metric is not exactly equivalent to the one with non-invertible metric, and again, as was discussed by Ramesh just now. In fact, the solution space for non-invertible metric possesses a much richer structure, and this is the work which Ramesh just described, and I have referred to Ramesh's talk here for more details. But these were not the people who discovered this fact first. Of course, there were these people who have thought about degenerate metric or tetrad configurations in gravity, and in particular this guy, Arkady Setlin, he had talked about a couple of solutions which are solutions of degenerate tetrad, and that was the first example which we could find, and that corresponds to the S3 geometry, one of the 8 geometries which Ramesh described. So these are the set of people, and of course one of them is sitting right here, Naresh. So now, the usual action principle for pure gravity in 4 dimensions is given in terms of the Einstein-Hilbert action. And that, as you can see, that requires the use of inverse metric, because this g mu nu, it's up and it's the inverse of the g mu nu down. However, in order to, and this is known as a metric or second order formulation, we all are familiar with. However, in order to deal with degenerate metrics or degenerate spacetimes in gravity theory, the appropriate starting point is to use an action principle that doesn't require the explicit use of the inverse metric.
Just this point that you said that inverse metric is required, that argument actually should go through that if you have g mu nu downstairs.
Yes.
You can write r mu nu upstairs, but that means r mu
nu needs some inversion. Yes. So we have to, in order to describe degenerate tetrad or metric configurations, we have to go to an action formulation that doesn't require this use of inverse metric. And of course, you know by now after Ramesh's talk that the appropriate starting point in order to describe such spacetimes is the first order action formulation, where the action is given in this form, where the symbols I am not going to explain again. This is the spacetime Levi-Civita, this is the internal Levi-Civita. Levi-Civita is the internal spacetime, and then these are the tetrads, and this is the curvature or tensor or the field strength associated with this gauge field or spin connection omega. And in the wedge notation, the same thing looks like this, where you take out this epsilon and put wedges, which means antisymmetric products. And this is known as the first order or Hilbert-Palatini formulation, where you don't require any inverse metric anywhere. And now this action is described in terms of two independent fields, the tetrad and spin connection. So in order to find the equations of motion, you have to vary this action with respect to both these sets of independent fields, and then you end up with these two sets of equations of motion. Now when tetrad is non-degenerate, these are equivalent to the Einstein's equations of motion, which means torsion is zero, it vanishes, and then you get the vanishing Ricci tensor.
Can I make a comment on this?
Yes.
You have varied the E and omega,
Yes.
as not insisting that they may be degenerate. Because if it were degenerate, the variations are restricted. I mean, you have to vary in a class of degenerate metrics. So you have to, but you have to impose a condition that determinant of E is.
There's no need for that.
So you're.
There's no need for.
You are doing a variation in the open set of all E's. Which
I don't completely understand what you mean and why you mean that, but then if you just simply take this action and you take variations of these two independent fields.
The variation allows non-degenerate metrics. Non-degenerate metrics. See, it's an open set.
What he means is that your E may be degenerate.
Yes.
When you write E plus delta E, that thing may not be degenerate.
E plus delta E also must be degenerate. So I am saying it for a particular reason, because this kind of problem appears in India, that the set of E's you are considering is a boundary of a manifold of E's, okay? And that boundary which you are considering here is a striated manifold. And in problems which I have done with Sachin and so on, what happens is that the operator which governs dynamics in the bulk, for that there are boundary conditions at this boundary in the striated manifold, and then in quantum theory you can get away with it. There is no problem.
Okay.
But the quantum theory is living in the bulk, but the operator is striated this.
Okay, so
forms
the upshot is that my maths is too weak in order to answer your question, so you fit your argument such that all this is bad. Then we can discuss the rest after the talk.
You can say that
Because-
start with the equations of motion.
In the
Supposing you
direction.
say you start with the equations of motion, and for degenerate it reduces to Einstein's equation, not degenerate. Now, what will happen if there is degenerate? So you can take that point
only
of
question
view.
So the variation is kept arbitrary.
What
Now,
they say is simple like this.
for arbitrary variations, I don't see any problem with this. Now,
But
That is
then
the problem.
assumes E is not degenerate.
okay.
It's not an arbitrary variation.
So you are saying delta is zero, then what happens? Is it
Not
those
zero,
directions,
not delta is zero.
if you just put that
Determinant is
in,
zero.
these
In S,
equations become
this is not
vacuous.
the equation.
That's the
We should
property of
consider
this.
all
They become
variations
vacuous.
such that determinant of E which you get all
That
the time
is
is always
the question is whether there is.
that is the class
more
of
to it.
variations you should.
Yeah, but where do I use that information here?
You use it.
I mean, when you vary, and then when you take out the variation part and separate out the rest, where do you use that property?
That is allowed only if the set of E's you are varying around are not subject to constraints like determinant of E being zero. Okay? For example, you have all kinds of actions where group elements enter, like SU2 group elements enter the action. Okay? Then you cannot vary G the group element arbitrarily. For
Okay.
example, SU2, you have to make sure that it is determinant of G is 1, G dagger G equal to 1.
Okay.
The variation. But you are not doing it. I am not objecting to it. But what happens in quantum theory in cases we have examined is that they come, this is okay.
In the quantum theory.
They come as boundaries of the open set of non-trivial E's. Quantum theory lives there, but there are differential operators, and you have to put appropriate boundary conditions to make them self-adjoint, and that is how the boundary enters.
Okay.
Okay, I am just making it. So the classical theory, quantum theory, in the case we have examined, does not go exactly like this.
Okay, I think
All
we
right.
can go ahead.
Fine.
Go ahead. Go
Point
ahead.
noted. So now, let's deal with this classical theory coming from this action, and then let's see what this simple variation gives. And I don't have to tell you because Ramesh has already told you. When metric is invertible, then you land up with the standard Einstein gravity, where the Ricci tensor vanishes, and the torsion also vanishes. However, when the tetrad is not invertible, then the theory doesn't reduce to Einstein gravity. And in that case, the equations, which are these two sets of equations of motion, they admit solutions with torsion, even in the absence of any matter coupling which can induce torsion, like fermions. And such solutions are not captured by metric formulation. That's the important point. Now, in view of this, it is also not clear whether curvature singularities, as we have seen, for example, Schwarzschild geometry is associated with a curvature singularity. So, whether such curvature singularities are an inevitable feature of non-trivial vacuum solutions in gravity theory with non-invertible tetrads. Yes, they are features of non-trivial vacuum solutions with invertible tetrads, but otherwise it's not very clear. What happens when you go to non-invertible tetrads? So the question we are going to ask, and then we are going to chase in this talk, is that, is it possible to find non-trivial vacuum solutions with well-behaved curvature components everywhere? I will make it more precise later. Exploiting the richer solution space for non-invertible tetrads. And that's why the machinery which Ramesh described, that will come into play. For example, can one construct a solution of equations of motion such that the exterior geometry is Schwarzschild, whereas the interior spacetime is non-singular in this above sense, where the curvature tensors are perfectly regular everywhere, including at the origin? Can you find such a solution? Because it's not necessarily true that everything has to correspond to the invertible case. So this is a question. Now, such an interior metric must be non-invertible, because we know that any invertible metric, if we take any invertible metric at the interior, then that should correspond to a singular curvature components. So that's the only window we have. So now let's go to this problem and make it and formulate it precisely. So we will work with the Schwarzschild case, where the exterior spacetime would be described by the Schwarzschild geometry. So let's recall that the static spherically symmetric solution outside of mass m is given by the Schwarzschild metric. You all know this form, where this r is the radial coordinate. And this is a solution, of course, of the Einstein's equation in vacuum, which you get for invertible tetrads. Now this metric, although it's an exterior solution, it remains a solution even inside the horizon, which is this boundary r equal to 2m, but not at the origin, because curvature tensors blow up there and the scalars blow up there. And precisely the quadratic curvature invariant has this form, where you can see explicitly that at r equal to 0 it's divergent. So our goal is to explore if it is possible to find well-behaved interior spacetimes with degenerate tetra, which can be joined smoothly across the horizon with the exterior Schwarzschild metric. And as a first step, one has to find a convenient reparametrization of Schwarzschild coordinates, for which the interior and exterior geometries can be compared and then joined smoothly. We need some universal coordinate system for both sides across the horizon. Yes.
So you are ignoring the interior Schwarzschild solution in some sense.
Yeah.
You are ignoring the metric.
Yes, I have Schwarzschild only at the exterior, and I have something different at the interior, which I will describe, and that will be modeled with a degenerate geometry.
But isn't it already expected? Because we know that when we cross the horizon.
Only horizon is degenerate, but not the interior.
But we also know that when we cross the horizon from outside, our timeline and space line
They flip.
change.
Yes.
We already know that what Ramesh told now, already that you are seeing that structure, that time and space line things are.
No, that's not tied up with that anyway. What he said was that the time-like component goes to 0, and then all degenerate geometries can be modeled based upon that structure, which are the Sengupta spacetimes.
But doing that, will that
Now, what kind of space-time you can take inside and all, of course, that will fall into one of those classes which he described. But it's not clear from that what you have to do, how you are going to find the join the solution across the horizon to the Schwarzschild. What happens to the junction conditions? Are all the curvature scalars smoothly joined?
Those things to
Is there singularity at the origin with those configurations? All that is not clear from that, right?
one final question. Does it have any implications on the space-time that an infalling observer can see?
I will come to that. So as a first step, as I said, one has to find a convenient reparametrization of the Schwarzschild geometry. So let's do that. So this is the usual Schwarzschild metric. Now let us introduce a new coordinate u, which you can call radial coordinate if you wish. So this f is a function that reparametrizes as r to u. And this function f has a property that at this particular point u naught, this function has a value 2m. That means this u naught basically corresponds to the horizon, because this f is basically r. And then its derivative vanishes at the horizon. Of course, you can ask whether you can really find such functions. I will explicitly give you an example. Now, in this new coordinate q, the metric, when you just replace this r by u everywhere, then this metric looks like this, where you have a derivative on the u part, and then the rest of the things, r is replaced by u and this function. And the associated curvature components also you can compute, but you don't need to look at the details of those structures. All you need to notice is that at the horizon, those curvature components are this form, where the 0i components vanish at the horizon and the ij components are non-zero. We don't need to into any more details. If somebody needs, I can tell them later. And even for this reparametrized Schwarzschild, the Ricci tensor vanishes. And that reconfirms the fact that this reparametrized Schwarzschild geometry is also a vacuum solution of Einstein gravity.
That anyway it should be. It's a coordinate.
It should be, but it depends on what you have done with this coordinate transformation. What are the properties? So, yeah, it's not necessarily true always and everywhere.
So it's not a singular coordinate.
It is.
So
It is.
It is.
It is. At the horizon, it's singular. That's why I mentioned that.
It is.
Okay,
It is.
but-
It is.
Yes, why we using?
But anyway, let's not go into that, because that there are more structures and we can go into that if needed. So now at the exterior, this describes a perfectly vacuum solution of Einstein theory. And now we also have to choose this function f explicitly, the reparametrization function, and this is how we choose it. This is just the end result. Of course, it needs a lot more work than the way I have said it. So here this L is a integer which is constrained to be greater than 1, and notice that in these new coordinates now we can go to the Schwarzschild interior as well as to the exterior, because when u is less than u naught, this describes an interior space-time, because this f is less than 2m and f is this r. So you are at the interior then. If u is greater than u naught, then this f is greater than 2m and you are at the Schwarzschild, outside the horizon. And this u0 means f is 0, which means r is 0. That means you are at the Schwarzschild origin. So with this you know actually where you are in terms of Schwarzschild geometry.
But no, for this FU, but when U is less than U naught,
Yes.
the interior is also vacuum. It's just a vacuum solution.
Yes, it's still, but we are not going to use it at the interior as a solution. We are going to use something different.
Yeah.
But it is.
Yeah.
It is. Yes. The point is that you can go to the interior all the way up to origin with these u coordinates. Now, we have constructed, we have not constructed, we have rephrased the exterior geometry in terms of this reparameterization. Now let us go to the main thing, which is how to construct a suitable interior geometry or space-time. So for the interior, which means we are at u less than or equal to u naught is the horizon, we consider a degenerate metric where the time component is 0 and it has the topology S2 cross R. And the two sphere is this part, theta and phi, and the R part is this u coordinate, which is the apparent radial coordinate. Now you can clearly see what are the tetrad configurations for this metric. So you write them down. One of them is 0, so it has 1 0 eigenvalue. Next, it's not all, it's first order framework, so there are other sets of independent fields which are the spin connections. So in order to find a complete configuration, we have to also specify the spin connections, such that this set tetrad and spin connection together, they satisfy the two sets of equations of motion which we obtained after variation. Now, it's not possible to give all the details that what and why, but I will give you the bare essentials of the choices involved here, how you can choose the spin connections. So we choose the time components to be 0, and regarding the spatial components, we choose half of them to be 0 and another half to be non-zero. And these are the spatial parts of the spin connection where one has the torsionless part and then one has some extra part. And I have made all the rest to be 0. This is our choice, such that it has to satisfy these equations of motion. Now, provided that so I have parameterized these 9 components of the spin connections in terms of the symmetric n-scale matrix. And this is the same n-scale which Ramesh also used in his talk. Now, so if this n-scale is symmetric, one can check that this set of spin connections along with this set of tetrads, they solve this first set of equations of motion, which is E wedge torsion equal to 0. We still have to satisfy the second one, and I am coming to that. So we have essentially, in this parameterization, we have essentially used this this n-scale matrix, which is symmetric. That means it has 6 independent components. And these 6 independent components essentially capture the torsional degrees of freedom, because this is the non-torsional, this is the torsional part and this is the non-torsional part. This is the Levi-Civita connection. So this quantifies the torsion in this theory. Now, the most general parameterization of this torsion or contortion matrix rather, it can be of this form, where you have 6 independent components and it is symmetric. However, we will go to a very simple ansatz, where 5 of the 6 components are chosen to be 0 and only one of them is non-zero. And also that is a function of only of the radial coordinate. In general, it can be a function of all the 4 coordinates, space-time coordinates. So this is a choice. And now, remember, among the 2 sets of equations of motion, these configurations already satisfy the first set. That's the choice we made earlier. Now we also have to satisfy this one. Now this set of equations of motion is also satisfied provided we have the following, this relation among these contortion variables and the metric fields F and H which appear in the metric. This F and H. So all the equations of motion are satisfied provided we have a constraint among the contortion variable eta1 and the metric fields F and H. And I call this as some master constraint. We don't need this detailed form. So I call this equation as some constraint C, depending upon the three variables. Now, let us go back to our original motivation, which was to reformulate now in terms of these variables, is that how to choose these three functions eta1, F and H such that this master constraint is satisfied. Of course, that has to be satisfied in order for that to be a solution of equations of motion. And secondly, we should be able to match the interior and exterior space-time in some way so that they are joined smoothly across the horizon. And that means the interior space-time, which is described by a degenerate metric, and the exterior geometry, which is described by the Schwarzschild metric, can be joined smoothly at the horizon. How to do that? That is a problem. So now we have already computed what are the curvature scalars at the exterior, which is Schwarzschild. Now let us, I have given you the set of fields for the interior degenerate geometry. Let's compute the curvature tensors for this interior space-time. So this is how they look like. They have certain expressions in terms of the three fields eta1, which is the torsion field, and the metric fields H and F. And of course, these three fields satisfy this master constraint. Don't forget that. Now, this master constraint provides only one condition among the three functions. So we have the freedom of choosing two other conditions in order to fix this three functions completely. So that means we have to choose the two conditions judiciously so that the two geometries are joined smoothly across the horizon. Now, that choice can be made if we have this. So we choose these two conditions where this functions, contortion function eta1 is related to the metric functions H and F in this way, and these functions H and F, they have this behavior. And this has a reason because they have to behave nicely at the horizon and they have to join smoothly across the horizon. So that's why it needs some understanding, but this is the end result. Remember, this U0 is the horizon. Now for this choice, so these two conditions along with the third one, which is a master constraint, they provide now three conditions for these three functions. So you can solve this theory and find these things explicitly and see whether what you want, that is what you are getting. So for this choice of functions, the interior curvature components of the horizon, they become like this, where some of them are 0 and some of them are non-zero. And they are fairly simple. All the rest are 0, of course, whatever I have written. In fact, I have written all of them. These are the 0 components, these are the ij components. Now,
this dot means
the dot means only at the horizon, not everywhere, because we have to compare this with the exterior Schwarzschild components at the horizon.
But are you saying that at the horizon all these components are 0?
Not all. Some of them are non-zero.
Oh, there is
Most of them are 0, but not all of them. Yes. They don't necessarily be non-zero also.
Right,
I mean, they don't have to be.
Right.
Now, all we have to do is to compare this curvature components which we have gotten from this interior construction to the exterior curvature components which we have already calculated for the Schwarzschild case, and or rather the reparameterized Schwarzschild case. And the Schwarzschild case gives these curvature components, and notice that these are exactly the same. at the horizon.
But this,
One.
But which boundary condition demands this that the curvature components will continue?
No, they are the gauge covariant objects in this first order framework. So
Okay.
you have to match. Yeah.
So I would like to see. So how will it translate in my usual junction condition where you
Usual junction conditions need the use of inverse metric. So that question, that's why you have to reformulate it, because that is in terms of extrinsic curvature and the metric.
So far
Yes, here the metric will match, you will see finally.
Metric will match.
Yes, but then you need something else also, which are these gauge covariant objects.
This is that. This is
Yes,
the-
yes.
Right.
And that is tailored to this first order
Right,
framework.
absolutely.
So, the remarkable thing is, you with this choice of conditions, suitably you can match these two curvature components at the horizon. Okay, but still it's not, your job is not over. So, okay, the curvature components are continuous across the horizon. That is one property we wanted. Now, the two conditions and the master constraint provide three equations, as I already mentioned, for the three variables. So, you can now explicitly solve these three variables in terms of the coordinates. And the result is that you end up with this form, where the metric functions f and h have this kind of an expression. And of course, the contortion variable also now is given it complete. So you have solved these variables and you have completed the construction of the interior spacetime as a vacuum solution of pure gravity. And this corresponds to this interior metric, where the time component is 0, and in the spatial parts f is given by this, h is given by this, and h is the radius of the two sphere. The two metrics, which means the degenerate metric at the interior and the Schwarzschild metric at the exterior, they are also continuous across the at the horizon. Now, yes, you have constructed a solution, but what about the behavior of the curvature components, which is problematic for the usual Schwarzschild interior? You notice that all the curvature components, sorry, this would be mu nu, I mean that means space and time.
Yeah.
This is a typo. Here, for this geometry we have constructed, all the curvature components are finite everywhere, even at the origin, u equal to 0. I can't give all the expressions which are very detailed, but you can check that. And that is unlike the usual Schwarzschild case. In Schwarzschild case, all these, in fact, almost each of them, barring one, which is 0, they all blow up at the origin. The Ricci scalar associated with the interior 3 geometry vanishes, which is similar to what you have in Schwarzschild case, because in Schwarzschild case, of course, you have the inverse 4 matrix. Here you can't have the inverse, so you can take the non-trivial 3 part of the geometry, which is R cross S2, and compute the corresponding scalars. So
this is 0 even at R equals 0?
Yes, everywhere. All these expressions, I mean everywhere.
No, because strictly speaking, in the standard Einsteinian general relativity, the R mu nu cannot be 0 at R equals 0, because there is a mass sitting there. So
It is not R mu nu, it is a scalar.
I
Remember.
agree. Here it
Yes.
is.
But R mu nus are not 0, they are finite in general, but not 0.
No, but in the Schwarzschild interior,
Yes,
the 3 scalar doesn't vanish.
it does.
No, in the Schwarzschild, why should it vanish in the interior? See, interior you have.
Not the 3 scale. In the Schwarzschild case, it's a full scalar that vanishes.
No, what I mean. By Schwarzschild interior, we mean the Schwarzschild interior solution.
Yes.
No, the Schwarzschild interior solution has the metal density and pressure.
Oh, okay. That is something different,
So
right?
what is the Schwarzschild? What do you mean by Schwarzschild interior?
That is a different solution than what I'm talking about here. That's
So what is Schwarzschild interior?
Schwarzschild interior is the same Schwarzschild metric, just continued inside.
You're
That's different than what
you
you
mean. U less than U
Yes,
naught.
yes, yes, yes,
U less than U naught.
yes, yes. Now,
2
the
minutes.
yes,
2 more
2 minutes. Okay. Let's go to the quadratic curvature invariant corresponding to this 3 geometry. Actually, I should have put some 3 here to distinguish it, but again, I'm saying it in words. This scalar, because that's all you can construct in this for this interior 3 geometry, and that is also that has this form, and this never goes to 0, even not at u equal to 0. This is finite everywhere at the interior, and of course exterior is Schwarzschild. So even this quadratic curvature scalar is finite corresponding to the 3 geometry. And the reason is that HU remains finite and non-zero everywhere at the Schwarzschild interior. So again, this regular behavior is unlike the usual Schwarzschild solution where it blows up at the origin. Even so, there the 4 curvature scalar, quadratic one, that also blows up, and even the 3 curvature scalar for Schwarzschild case, even that blows up. Both have this behavior. So in both sense, this is an improved behavior without any singularity apparently. So now this is what I wanted to talk about mainly. Now let's summarize. So we have completed the exercise we wanted to do. We have found a class of non-trivial vacuum solutions in gravity theory corresponding to an interior region with degenerate tetra and an exterior spacetime with the Schwarzschild geometry. All the curvature tensor components are continuous across the horizon, and so is the metric. These solutions are well behaved everywhere in the sense that all the curvature tensor components individually are finite everywhere. 1. Also, all the 3 curvature scalars associated with the non-degenerate R cross S2 subspace, or the 3 subspace of the degenerate 4 spacetime at the interior, are finite everywhere, including at the origin. And another important fact to notice is that you have the Schwarzschild mass parameter at the exterior geometry, but now you have no matter inside. So what is the interpretation? It has a purely torsional origin. So this mass doesn't come from any matter inside, unlike the usual Schwarzschild interpretation. So this is very much incomplete. So there are many issues to be explored, but just to mention a few, one can of course find out how do the geodesics behave in this spacetimes, which are some new kinds of solutions in vacuum solutions in general relativity, and of course that is in progress. And as you know by now, how should they affect the analysis of quantum gravity? Because Ramesh also mentioned that these configurations are zero action configurations. Even these ones are zero action configurations, because exterior is Schwarzschild, that has zero action, interior is degenerate, that has zero action, and at the horizon they join smoothly. So these are finite action configurations, and they should they should contribute non-trivially in the path integral if you do that exercise for quantum gravity. So what happens there, and how do we modify our notion of what is the right vacuum in quantum gravity, etc.? All those questions are relevant here, but I don't want to go into too much of speculation and such details. So yeah.
I had a question.
Could I just ask about the last thing you said about the geodesic? I'm not even sure what it means for. Consider the problem of an observer falling into a Schwarzschild black hole.
Yes.
I'm not even sure what it means when the space is degenerate. How does one continue a timeline, even continue a timeline geodesic itself?
Yes.
So
I mean.
So I don't even see how one can start to answer that.
Yes, that's a non-trivial question, and yes, I agree, and I am yet to understand this.
This is the same problem as how does the particle move?
Yes.
So,
Or coupled fields.
particle inside the particle moves for whom the time is zero.
then
That's-
what do you do? It doesn't
Well,
know.
that's right, that's the question is,
Okay,
how
okay.
to decide, call it.
No, 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 I'm the
how to
chair.
make it move.
I'm the chair.
Sorry.
Next
So,
question.
a related question. So, in this, it's not even clear that U equal to U0 is a horizon in the sense of one-way membrane, because you don't know about the geodesic. So, and since the metric is degenerate, one at the moment is not seeing whether a null ray can come out of U equal to U0 or not.
Absolutely. So that's why I restrict to this thing that it's only the location of the Schwarzschild horizon. That's all I mean here.
Okay, next question.
I have just a question. While you are calculating your equation of motion, you are varying with respect to the tetrad.
Yes.
But the tetrad satisfies the condition determinant equal to 0.
It may or may not. It's for the most general case.
No.
In this case, yes, that case is included.
So classically even, the components of the tetrad are not independent.
Are not?
Are not independent.
Or not independent.
Why?
Determinant is 0.
So how can you vary?
So,
You should
some
actually
function of the
use some
multiplier.
Lagrange multiplier.
But then when you vary, you don't impose these conditions, right? You vary as if they are completely arbitrary.
That is
Then you are not
That is
taking-
my
So
problem.
is it the confusion between some kind of on-shell variation and off-shell variation?
So the question is how many degrees of freedom?
No.
Then you are not saying
Same
that
question.
tetrad is zero.
Yeah, that is related to Ball's question again, and I don't understand that issue completely. So
Next.
I can't answer
We
that.
should go to the coffee.
Yes.
Right.
So, you mentioned that the geodesic investigation is ongoing, but still I was curious as to whether some understanding has been obtained. Like say,
Nothing has been obtained. Now ask your question.
time like geodesic, if it reaches, it's an infalling field, it reaches the horizon. And after that, is there some complication in the solving the
Geometry
geodesic equation since the metric is degenerate?
Again, without doing computations, I can't say anything about that.
Okay, last question.
Suppose you start with a regular coordinate system like this analysis and go through all these steps. Do you get the same?
No, this exercise I wanted to repeat with Kruskal also, and it should go through. All you, why I chose this set of coordinates like you, is that you should need some universal system in which you should compare both.
Crystal outside.
Kruskal outside, yes.
Okay, anyhow, last one. You have been asked.
Yeah, it looks like actually time is stopping at the horizon and then you've got it continuously vanishing, actually non-existent in the interior. So a geodesic actually is not going to have any dynamics as far as, it's not going to actually fall in, it just is frozen there. That's why I was asking you about the infalling observer.
I don't know, because in the usual Schwarzschild geometry, your space becomes time. So now you already have a spatial coordinate sitting there which can play the role of a time. So you don't know what is happening there. Don't be so careless.
Geodesics have to be worked on. Okay, next.